Hello everyone, I welcome you to my research presentation. I am Nadashree Bose and I will be presenting on optimizing healthcare analytics, a zero-inflated Poisson approach to pediatric emergency room visits. This research focuses on regression modeling. This will be the flow of my presentation. First, the question comes, what is count data? Count data is a statistical data type describing countable quantities which can take only the counting numbers or non-negative integers. In various fields, accurate modeling of count data in which the dependent variables contains an excess of zero-value data is crucial for meaningful analysis. The Poisson regression model is a common tool for count data which assumes that the mean and variance are equal, but this assumption is frequently violated in practical situations due to the turning up of excessive zeros in the data. Overdispersion occurs when the variance exceeds the nominal mean, which is a common issue in count data modeling. So, in this scenario, the zero-inflated Poisson regression model is a suitable alternative when overdispersion occurs by an excessive number of zero counts. This model has the advantage of categorizing the population into two groups, one with zero outcomes and the other with non-zero outcomes. We will come to this in later slides. This study's research question is going to center on how well the Poisson regression model and the zero-inflated Poisson regression model perform when analyzing count data, with a particular emphasis on overdispersion brought on by an excessive number of zero counts. We want to check which model is more suitable for addressing the observed characteristics of count data, particularly in context of hospital emergency room visits by children aged between 10 to 18 years. So the objective of the study is to evaluate and compare the performance of the Poisson regression model and the zero-inflated Poisson regression model in modeling count data using the mean squared error as a comparative metric and applying them to analyze the frequency of hospital emergency room visits by children aged between 10 to 18 years. Our final goal is to determine which model better addresses the specific feature of the dataset, especially the overdispersion caused by an excess of zero counts. Coming to research methodology, what is GLM? That is a generalized linear regression model. Is made up of three components: a random component which defines the conditional distribution of dependent variable y within the exponential family such as binomial, gamma, Poisson, Gaussian, etc., given the values of the independent variables in the model. A linear predictor which is a linear function of explanatory variables and is given by this form. And third is a link function which can be inverted, which establishes a connection between the mean of the response variable to the linear predictor and is given by this form. Poisson regression is a common method for modeling data for counts. The Poisson regression takes this form and has equal mean and variance. By Fisher scoring method, the Poisson maximum likelihood estimator can be estimated and will be of this form. Now for modeling zero inflation in count data, zero-inflated Poisson model can be thought of as a mixing model. There are two categories of zeros that can be identified in the count data for the zero-inflated Poisson model. The first one is known as structural zero, which belongs to a non-susceptible group and it happens with a probability of pi. And the second is random zeros that come from a vulnerable group. The random zero has a Poisson distribution and occurs with probability 1 minus pi. This is the form of zero-inflated Poisson regression where pi I is the logistic link function. We can estimate the zero-inflated Poisson maximum likelihood estimator, that is ZPMLE, by simplex approach and will be of this form. The general form of MSE for Poisson MLE and ZPMLE is defined by this form. Next is data collection. So data source is the study utilizes the emergency room dataset sourced from NHIS 2022 US database. The primary focus of the study is on the count of emergency room visits made by children aged between 10 to 18 years within the preceding 12 months. And it comprises a total of 13 variables including 12 independent covariates and the target variable which is visits. and the sample size of the data set is 495 of children falling within the age group of 10 to 18 years. The relevant question is how frequently a child has visited a hospital emergency room for concerns about their health over the past 12 months. So detailed information about the 13 variables, including the independent and dependent variable visit, is provided in this table. So explaining the variable description, visits is emergency room visits by children between age 10 to 18. Sex explains gender of the child. Age explains age of the child. PH stat is general health status. Height is height of the child. Weight is weight of the child. BMI is body mass index of the child. Medication is child needed prescription medication but did not get it due to cost or not. Traffic is traffic causes safety issues in the neighborhood or not. Behavior is difficulty controlling behavior of the child or not. Dental is time since last dental exam or cleaning. Asthma is asthma emergency room visit by the child, and diabetes is child ever had diabetes or not. We can see that 61% of them are male and 39% are female from the data. Between the ages of 10 and 18, hospital emergency room visits by children have a mean of 0.35 and a standard deviation of 0.95. Thus, the variance is significantly larger than the mean. This shows that the data is over-dispersed. Also, from this figure, we can see that the distribution of emergency room visits is shown, where the excess of zeros is clearly visible. So, a Poisson regression model is not the best model to fit the data in this scenario. These are the results of my research. These are the estimated tables for Poisson and zip regression models. The 12 independent variables that I discussed in the previous slides are encoded, and the regression is first performed with the new 39 variables. All the variables for the Poisson regression model and the count part of the zero-inflated Poisson regression model are significant based on the p-value as it is less than 0.05. So the performance of these models are evaluated in terms of MSE value and AIC value. We can see that the MSE value for zip model is 0.3, whereas for Poisson is 5.5. So we can see that zip regression model outperforms the Poisson regression model, which can be seen by its lower MSE. Also, the AIC for zip regression model is 661.08 and for Poisson is 677.38, so which is notably lower. So we can say that zip regression model is superior fit to the data. So in presence of over dispersion, a zip regression model better explains the excessive zeros than the general Poisson regression model. This is the count part of the zero-inflated Poisson regression model, which is given by this form. We can see that asthma and diabetes have positive signs, indicating that a positive change in these factors induces an increase in the number of visits to the emergency room by children of age 10 to 18 years. Similarly, we can interpret for rest of the covariates. By means of all these findings, it is simple to conclude that the zip regression model outperforms the Poisson regression model in terms of accurately predicting the quantity of visitors to a hospital's emergency room. This analysis underscores a key insight in discrete data scenarios where an overabundance of zero counts is observed in the dependent variable. The zip regression model consistently outperforms the Poisson regression model. Coming to conclusions, this research highlights the significance of count data modeling in various fields, particularly in public health. Poisson regression model often assumes uniform dispersion, which can be a limitation in real-world datasets. This study demonstrates that the zip regression model is a superior choice when dealing with over-dispersion caused by an excess of zero counts. Adopting this model can result in more precise and informative studies, which will ultimately improve healthcare decision-making and resource allocation in the public health sector. This is all from my side. Thank you.